Actually, you can find that on Google now, because I think that's probably the first thing I say in the talk that I gave on the ATRN network last week. Okay, so anyway, I'm going to be talking about fluid flows and studying them with persistent homology. We like a lot of variety in our workshop, so I thought I would give sort of the antithesis talk to the one that you just saw with Charlie. We have slides, we have real data. We are going to try to finish all the content that we produced. So I think we've gotten about as far away, so there's no comparisons allowed here. All right. So we are going to start by looking at, actually, this whole talk is really going to walk through a collection of applications. So we're going to look at applications to fluid flows covering the dynamics of the fluids. We're going to look at patterns of the fluids. Both of these first examples will be in two-dimensional fluid flow simulations. On the left, Kolmogorov flow, and on the right, Rayleigh-Bénard convection. Then we'll move into the three-dimensional case and study fully developed turbulence, and then also take a look at some problems in combustion. This is also three-dimensional combustion simulations. Okay, this is a lot of pretty pictures and a lot of fluid flows. We're going to unify them in one additional way by using persistent homology in each one of these applications. Now, most people at this point in time would probably either say, well, first I'll start by introducing what persistent homology is, and I've decided I'm not going to do that because it's a lot like trying to describe what a Swiss Army knife is. Is it a pocket knife? Sure, it is many other things. So we're going to look at how persistent homology is used in many different contexts. So by the end, hopefully we'll all have an idea of what persistent homology is, so to speak. So the first case we're going to check out, and I hit the wrong button, is dynamics. So Act 1, this is actually some work that was done a little while ago, but it really sets the stage and builds out the foundation for a lot of the work that comes next. So this is analyzing Kolmogorov flow and Rayleigh-Bénard convection using persistence. So first we have our simulation of two-dimensional Kolmogorov flow. It comes from the Kolmogorov model. I'm not going to go through and define each of these equations because this will take probably a third of the talk. Z component of vorticity is really what we're looking at. So vorticity, think about when you have a whirlpool in a fluid, how much spin you have at any given point is going to be the vorticity. And the Z component in this case, well, that will give you a direction. Are spinning counterclockwise, counterclockwise white pointing up, or clockwise pointing down. And so that's what we're looking at. Now, this is not fluid flow on a square. This is actually fluid flow on a torus. And so we've got these periodic boundary conditions, the top and the bottom of the picture identified. You can see how the picture actually lines up, and then on the left and right. So it's a two-dimensional fluid flow on the surface of a torus. But now we've got all of these different symmetry relations. Then the equation at the bottom is invariant under these different translations. So at the top we've got translation in the x direction. We've got a rotation, reflection about the origin, and then a reflection rotation. So how do we deal with these symmetries? Let me start the video here. I should point this over here. So this is actually a periodic orbit of some sort. Over on the right, you've got a projection of this system to the first three imaginary Fourier modes. And you can see that this cylinder is slowly being traced out. So where we started up here at the left, you've got this pattern, and we'll get there just about now. By the time you get around to the opposite side of this cylinder, you've got quite a different pattern. And then if we played time forward way in advance and we traversed down this cylinder, you would end up with a pattern very similar to the one you started with, but it's shifted over in the x direction. And so you can see how those black and white local minima and local maxima are translated in the x direction. So we want to know, well, can we study the dynamics in the relative periodic sense? Can we quotient out all of these different symmetries and look to see what our dynamics are doing? So I mentioned we were going to be using some persistent homology. It only took us 2 slides to get there. We're going to use persistent homology to do this quotienting out of the symmetries. So how does this work? We've got our fluid flow on a torus on the left, just a single picture. what we're going to do is sublevel set persistent homology. So this threshold omega for the vorticity, it's going to start at a very low value and then slowly increase, and we're going to look at the sublevel sets. And as the sublevel sets change, we're going to keep track of their zero-dimensional and first-dimensional homology. So that's this line over to the left. Well, eventually we'll pass these local minima. So we've got two connected components, two more have popped in. The persistence diagrams, right, are a representation of the barcode in the bottom that's being swept out. Eventually we hit some saddle points. Connected components start merging. Bars are born. And now we see these persistence points in the quadrants represent these 8 bars, 4 in dimension 0, 4 in dimension 1. Now we only have the loops. There's not 8 loops, though there's actually 9. We've got 8 local maxima. Now we have even fewer. And at the very end, you end up with the essential homology classes of the torus. So at the very end, in the limit, you've got 1 connected component on the torus and then 2 loops of the torus. And then in between, all of the persistent homology. So for those who are familiar with persistence module theory, what you see at the bottom, essentially, you've got a functor from the real line in this case to finite dimensional vector spaces. And the idea is, along each real number here, you're going to record the vector space given by the homology of the sublevel set at that value. And then this decomposition is actually the Kroll-Schmidt decomposition of these modules. And so think about it as, when you're doing data analysis, maybe the persistence diagrams up on the right are very convenient to work with, but underlying all of this, you have a rich algebraic structure, the persistence module at the bottom. All right, I mentioned we're going to remove symmetries by doing this. We did automatically. If we apply any homeomorphism to the domain before looking at our scalar field, it's going to be, our homology is going to be invariant to that. So these translations on the torus, we're not going to see any of that. All right. We're going to need to compare persistence diagrams. And this will help us see, okay, well, we know how to take a persistence diagram of a single scalar field, but what if we quotiented out what's really invariant? The metric we're going to use is called the bottleneck distance metric. So if you have a blue persistence diagram and a black persistence diagram, how do you compare the similarity or difference between them? And it's sort of a minimax theorem. So you match the points in the diagrams. If the points are, maybe there's a different number of points, you can always match to the diagonal orthogonally, and then you want to take the maximum distance between that matching, and then take the infimum of that maximum distance over all possible matchings. So that gives you, in a sense, the largest difference between two persistence diagrams. Now, we've got A and B are those samples from along that periodic orbit, or shifted periodic orbit. And those are going to be represented by the circle and the plus. So you've got these little targets where you can see these persistence diagrams sit almost exactly on top of each other. But then this one on the right, C, a very different pattern to our eye, also a different pattern on the persistence plane. And then you can see the bottleneck distance between A and B or A and C are quite different. Where A and B, that difference is really on the scale of perhaps error inherent in the numerical simulation or the discretization of the pixels in the domain. We're going to now look at a different instantiation of persistent homology, point cloud persistent homology. So given points in a metric space, you can compute its persistence diagram. We're also just looking at dimension 0 and dimension 1 here. And you do this by inflating the set with balls of radius epsilon, and then tracking the connected components and the loop structures as those balls grow. And we can sweep backwards and see eventually this hole will reappear. We're now on this large bar. Eventually, this point cloud will break apart again. And so now we can see that if we had sampled points from an annulus or a circle, we can sort of read these persistence diagrams on the right as a persistent homology signature of a circle. Now, something I really want to call out, oops, I always hit the wrong button. What I want to call out is that at the time, or approximately the time, when your point cloud coalesces, or at the radius that it coalesces into a single structure, this is when our circle is born. So you take this last finite persistence point, traverse over to the right, and that's approximately when the circle was born. So we didn't have, say, a C shape. We know that it was approximately a circle. So when we're looking for, say, periodic orbits that sweep out perhaps a circular shape, we're going to be looking for this signature of a circle. So back to our Kolmogorov situation. We've got our persistence diagrams, our points moving around. This is our bottleneck distance matrix. So here you can just see the pairwise bottleneck distance between all of our 500 sample points along the trajectory. And then here's our cylinder being swept out. So what we don't know is after we quotient out all these different symmetries, how tangled is this cylinder going to be? I mean, in this one representation, it's cylindrical, but perhaps it could have gotten very tangled after identifying all the symmetries. So, well, we use this distance matrix to treat all of these persistence diagrams as a point cloud sampled in the space of persistence diagrams along this trajectory, and we compute the persistence diagram. And sure enough, we see this signature of a circle from the persistence diagram. So we see that persistent homology, at least in this case, it does a good job at reducing our symmetries, and then thankfully doesn't collapse so much. You're not losing so much information that you are tangling up your periodic trajectory. Yes?
I'm sorry, what is a sample point? Is it a point in the flow? Is it one of the points in the...
It started as a point, as a picture. It started as one of these images with periodic boundary conditions. Then it was mapped to a vector of persistence diagrams. And then, yeah.
So that picture in the upper left is one sample point?
Yes,
okay.
Exactly.
Okay.
Exactly. And then we take 500, a time series of 500 of those. Yeah.
What's the color indicating omega?
That's the vorticity. So from,
that's how swirl.
Yep, counterclockwise and clockwise swirling. Exactly. All right.
Down below in the lower one? Color down there?
On the left?
That's just the bottleneck distance?
This is bottleneck distance. So I hoped to move past this point very quickly. This is actually the persistence of a point cloud according to what's called Wasserstein distance. And this is bottleneck distance. These are on different scales. I couldn't find the pictures that corresponded. So pretend like this is a larger, it's farther away from the diagonal. Man, I was like really hoping we'd go right by that. Yeah?
I guess I'm puzzled by that picture in the lower left. Maybe you don't want me to think about it, but...
The bottleneck distance?
Yeah, it seems like these sample points look very similar in terms of their homology. So why can't you get such different?
So this is the bottleneck distance between pairwise selections of persistence diagrams. So you see this black line along the diagonal is distance 0. That's because every point is distance 0 from itself.
Right, but it seems like, I mean, what's the scale on that picture?
It's normalized to 1. So bottleneck distance is 1. Yeah. Anyway, I want to make sure we get to the exciting stuff at the end, because I promised I would get to the end. Okay, so we've got Rayleigh-Bénard convection now instead. So in this case, we have another two-dimensional fluid flow. This does not have periodic boundary conditions. And the schematic on the bottom shows essentially what's happening. You have a shallow layer of fluid being heated from below and cooled from above. And we're taking the mid-plane temperature of it. So here you can see there are cold, falling fluid, that's going to be black. And then hot, rising fluid is going to be the white and the yellow. And we have another periodic phenomenon happening here, this pinch off in the middle of this roll. So it squeezes, squeezes, squeezes. Once we get to this discontinuity sort of, these persistence points start moving very fast. It pinches off, and now you have a black roll in the middle. And then that black one will pinch off, and you'll have a white one in the middle. So it alternates sort of a two-stage periodic dynamics. Now the problem is this fast and slow time scales is giving us problems here. So imagine you've got these slow-moving dynamics. This is the squeezing regime that we're in right now. And then on the other boundaries, we've got these fast-moving dynamics, or these pinch-offs. if we sample this trajectory uniformly in time, you can do just fine on your slow-moving dynamics, but once you get to the fast-moving dynamics, if you don't change your speed, you might miss the edges entirely, and that's actually what's happening here. So we're completely missing the edges. You have some evidence by just the checkerboardy shape here, but more importantly, when you run the persistence computation and try to find the circle, you have coalescence, and these scales do match. You have coalescence into a single dynamical structure at radius 20, so diameter 40. The entire point cloud has diameter 100. So this is a pretty significant chunk that's missing, perhaps. Now, you do have this loop that's born at the right time, but you can't really rely on it or say much about it. So what did we end up doing? This is our original setup. We kept uniform sampling, but we went over more periods and then just went crazy with the number of sample points. So we started with only 500 samples. Now we have 70,000 sample points. So 70,000 different images we're going to process. But our maximum consecutive bottleneck distance between persistence diagrams has dropped from 83 down to 4. So we know we've got some really good sampling now. This is way too big for any computer out there at the moment. So we have to subsample the point cloud. So we sparsify it and say, well, I'm going to choose some covering of points so that I know that, well, every single point of my subsample is distance 4.5 away from the original. And that actually thins it out considerably. There's only 523 samples left. And here is the resulting persistence diagram. You have coalescence into a single structure at radius 4.5 or so, and that's when that first loop is born. But then you do see actually a second one. So maybe this periodic orbit in the space of persistence diagrams is twisted or bent or distorted in some way. So these gray boxes have to do with the fact that we subsampled the point cloud. So we no longer have precise location from that true sampling. Using the bottleneck distance, we can place these dashed lines on the image as our air bounds. And what I want to give you a glimpse of next is some of the theoretical work that came out of this application to actually go through and try and find better ways to express rigorous errors. And so this is just basically a one-slide video, let's say, of a recent work that we just put on the archive, tracking errors in the space of persistence diagrams. And this is work with Sean Harker, Miro Kramer, and Konstantin. So in general, the paper has in it an algebraic stability theorem for generalized interleavings. It doesn't really matter what that is. Here are some pictures. So our persistence module along the top gives rise to some persistence diagram. This is the thing that we can compute. And we want to know, well, what if we have this theoretical persistence module we couldn't get our hands on? Where would its corresponding persistence point be? Well, you relate these two persistence modules with something called an interleaving. And at the level of the linear algebra, these are linear maps that go from top to bottom and bottom to top, such that the upper triangle commutes, and then likewise so that the lower triangle commutes, plus some other commutative relations. But this is the main idea. So if I have all of these maps, and they're everywhere between these two persistence modules, and I have this epsilon situation, then I recover this bottleneck distance bound, where my true point from my true persistence module W sits somewhere inside of this box of radius epsilon. We can generalize this for generalized interleavings, express this point now as B comma D, and instead of shifting forward by T plus epsilon, we have some translation map tau in pink, and some other translation map sigma in blue. So this tells you how much, in a monotone increasing way, do you jump forward whenever you map from bottom to top or top to bottom. And these actually control the lower left corner and the upper right corner of where those bounding boxes are in the persistence plane. And so now it's possible that these are not just a constant shift T plus epsilon, but as this point moves around on the persistence plane, this box could really change shape depending on what those maps look like. In addition, like when you're thinning out a point cloud, you might have knocked away a lot of noise along the diagonal. This is all going to be trapped in this composition up here on W, tau composed sigma of S. And then any noise you might introduce, I don't have it drawn, it would actually be trapped inside of this composition. There's a really nice picture of what's going on when you want to use persistence and then possibly keep track of your errors rigorously that you're introducing into your system. Okay, Act 2, patterns. So now we're going to go back to Rayleigh-Bénard convection, but at a higher Rayleigh number. So things are going to get a lot more complicated than our simple pinch-off case. This is work that's currently in preparation, and it's pretty new, so I'm just going to give a flavor of the direction, and like I said, a way to use persistence. So on the left, we have our simulated Rayleigh-Bénard convection. I do have a Rayleigh number, 4,000, so pretty high. And this is highly sampled, so the pattern appears to be moving very, very slowly. This is because we have very, very high time resolution on what's going on here. And you can see that there's some sort of a signature of the pattern reflected in the persistence diagrams, and we want to get a better handle on that relationship. Why do we want to do that? So the problem from the physics community comes from essentially this observation back in 2000 that when you have this spiral defect chaos, the leading order Lyapunov vector will tell you where on the domain locally the pattern is most sensitive in, say, a local perturbation change, how that affects the long-term dynamics. And so on the right, they highlight, hey, this seems to happen wherever there's pinch-offs. Look, we're done. There's our Nature paper, and that's it. And now it's, 18 years later. And so we're like, well, let's flesh out the story a little bit, because we look on the video on the left, and there's lots more happening than just at pinch-offs. Yeah?
Wait, the pinch-off is the most or the least stable of perturbations?
It's not the pinch-off itself, it's the dynamics of the pattern. So if it's like sort of the butterfly effect, the way I think about it is if a butterfly flaps its wings right there, then the whole pattern is going to be different in the future.
That's the point of strongest butterfly.
Yeah, exactly. That's kind of how I think about it. I don't know. That's kind of a, intuition. Okay, so what we want to do is how can we relate these high magnitude spots in the leading order Lyapunov vector to observable pattern phenomena? So one way to do this is to, they talk about pinch-offs, but what about classical ways of describing a pattern in these locally striped type images or in Rayleigh-Bénard convection? So the classical way is to look at, say, concave disclinations and convex disclinations. These are like in your fingerprints, whorls and deltas. They are identified by taking the Poincare index of the orientation field. So imagine looking at level sets of these. You can follow the directions of the rolls. And this makes a single counterclockwise turn plus one, single clockwise turn, that'd be a -1. And then you can combine these to dislocations is going to be a pair of +1, -1s. Grain boundaries are a chain of +1, -1s. And then there's also targets and spirals are canonically identified in these patterns. And so this is pretty well studied in the locally striped pattern community. To identify targets and spirals, see they both have 2 +1s. We use persistent homology because why not? There are other ways, of course, to disambiguate these. But with ideal simulated patterns, of course, all you need to check to see is, well, one of them's on a black node and one of them's on a white one, and over here they're on the same color. But in real data, unfortunately, those points, the locations, move around a lot. And you might not be able to distinguish them that way. So the presence or absence of a circle, of a loop in persistence is actually a more robust way to do that. All right, so how are we going to get a handle on these patterns with persistence? Morse theory can be thought of as a way to take these critical points in our scalar field and then pair them in a way that then you can reconstruct the persistent homology. So over on the left, I've run a persistence algorithm, both from the sublevel sweeping up from the bottom perspective, and that is in red and cyan, and then also from the super level set perspective, so sweeping top to bottom, and that is in the blue and the pink. Now I have paired them in this sort of opposite way because you start to notice when you look at enough of these there's going to be some sort of a duality or correspondence between some of the pairings from the sublevel set perspective and some of them from superlevel set. So to watch this in action, this is you can think of this as the persistence of a volcano. We're going to start sweeping from top down. So here's our threshold at the top, and we're going to look at the shape, the topology of the yellow set. And we're first going to look at dimension 1, or loops. So our yellow is almost closing around on the back saddle point, and we can see it's encroaching on the saddle point on the left. So it's about ready to give birth to a dimension 1 superlevel set generator right there. And then as the superlevel set decreases, we'll get to that local minima in the center. And that will be the death critical cell of that superlevel dimension 1. Now let's go the opposite. Fix your eyes on this dark region in the center. A dimension 0 sublevel set component has been born, and then it will die when you get to that same saddle point that gave rise to the dimension 1 persistence. So this gives you a sense of how, not only are we showing, well, we can point out critical cells through persistent homology, but maybe we can actually look at some real patterns within these scalar fields as well through looking at some of these pairings and these correspondences. So the first thing, actually, we take kind of both of those statements and then focus on how are we going to focus on points of interest that we couldn't get from the other topological methods, so from the topological defects. And in this case, persistent homology gives us a way to choose specific saddle points that could be interesting and point to where roll pinch-offs occur. And it will also allow us to choose local estrema, which we'll call emerging targets. So these are like baby target patterns that are just starting to form, for instance. And these regions in the persistence plane are exactly how you can do that. So for a roll pinch-off, you would choose, well, what was that H0 death cell? As I go from bottom to top, it dies at a saddle point. As I go from H1 birth critical cell, top to bottom, I'm going to be born at a saddle point, and I want to pick that off in this gray region here. And then same for the roll pinch-offs. So now we've got a collection of additional points of interest that we might want to take a look at. So here's an idea of the direction we're headed. I wanted to put a little bit more of the recent results we have, but I was afraid we didn't quite have enough of the story to come together. So hopefully that will start to come together a little bit here in the future. But as an idea, so our Lyapunov vector magnitude is now in the white and the gray. So you can see these areas that are being highlighted in white. And we want to know we've talked about these first three, of these different annotations that we can put on the observables on the pattern, how can we figure out which ones, maybe through machine learning, some sort of statistical relationship between these observables and these high magnitude Lyapunov vector regions. So our topological defect creations, if you have a target that suddenly appears, 2 + 1 topological defects will appear, and they'll appear in cyan there. These topological defects are also moving around, so you can see there's shadows of defects with different, the faster they're moving, the more opaque they are. And then any of our persistent homology defects are in yellow, and lots of times they do correspond. High and low local wave number, these are more classical computations, so the pink will actually show where the rolls are spreading out and getting fatter, and then the reddish orange color will be where they're pinching off. So in lots of cases, our saddle points and our high local wave number will coincide because they both point to pinch-offs. But you can see there's lots of saddle points that aren't captured strictly by the high local wave number. So we're currently working on ways to quantify these relationships and try and tell a more complete picture and story than what Egolf left us with back in 2000. Now, one thing I want to point out are these emerging targets. Oh, does this actually, I have no mouse control apparently. You can see it up there. Okay, so this is really hard. That's impossible. Okay, so if we play it, the emerging targets, oh well, I've broken everything. Emerging targets, remember those were the ones the loops were being formed, essentially. That's what we want to focus on here. So one of them might be here, one of them might be here. When I play this video, over on the right we have 20 persistence diagrams superimposed on top of each other. And I will circle one of them, and then this is what's called the vine in the vineyard of persistence diagrams. So this is the terminology that's in the literature. A time series of persistence diagrams is a vineyard, and then each of these vines comprise the different paths across the plane that these persistence points take. So the question is, when you have vines that cross each other on the persistence plane, can you actually distinguish them at the level of the mathematics and the algebra underneath? And so in general, the answer is going to be no, but perhaps we can see with our eyes, these generators are very separate from one another. How far back do you need to go in order to disambiguate and to separate these pieces? So we'll take a look at that. Same flavor, or different flavor of the same problem. Here you've got simulated fluid flow on the left, and we wanted to know, well, what if we didn't have this high resolution data? What if we only have every 20 images? And then between every 20 images, we just linearly interpolate between the images, and we compare the paths on the persistence plane. So black is the true dynamics, and they tend to be a little bit more predictable. And then that linear interpolation kind of bounces off. So it acts as actually very wild compared to the quote-unquote true dynamics. And so the question is, let's say you had done some sort of continuation and run the Vineyard algorithm and tracked these points across the plane. How much did your choice of interpolation or your choice of algorithm affect that matching? And did you accidentally cross paths that you shouldn't have? And how robust are these matchings to homotopies or changes in the interpolation? So again, I just want to give you a flavor or a sense of some of the theoretical development that then came out of trying to answer this question. This is work that I'm currently doing with Justin Curry on the stability of persistence vineyards. So the idea here is to move beyond persistence modules, essentially. So up at the top, we have our set with two circles in it. We're going to look at the persistent homology of this set by inflating it by balls of radius epsilon, recording its barcode. So the two loops die almost immediately. They join into a single connected component, and that's the persistent homology of that set. Now we can actually record a little bit different structure. So this H0, these two barcodes, can actually be recorded in what's called the merge tree. And this will actually tell us which bar connected with which when it died. So now we've got our merge tree poset, and we can actually record our homology, in this case dimension 1 homology, but HN persistent homology, on the merge tree itself. And then in the language of category theory, the persistence module would then be the push forward of this merge tree along that height function. And so everything would just direct sum vertically, and we all know that the direct sum of disjoint, if you take the homology of a direct sum of topological spaces, then you'll have the direct sum of the homology. And so that's essentially what's in there. It's not very deep, but it's potentially useful. And then as far as the vines are concerned, if they stay on distinct branches, while this is all moving around, then they can definitely be disambiguated. So this is just a first glimpse. We're looking at not just the H1 decorated merge tree, but how can you extend this to, say, Rabe graphs or other topological structures that can be pulled out of the filtrations, let's say. So that's exciting work. So Act 3, turbulence. So now we're leaving the world of the patterns. In a sense, this is going to be a look into how persistence can be used for data organization, big data problems, really, if we want to use the fancy words. And this is a really exciting collaboration. Hopefully it will be available for people to see this year. I think it's getting close, and it's pretty exciting work. So we've got this really giant data set. Navier-Stokes equations, three-dimensional direct numerical simulation. What you see on the left is the magnitude of the vorticity field. So just like with Kolmogorov, we're looking at the spin of the whirlpools. Each bit of this tiny variation in this picture is a different whirlpool. So if you're familiar with physics length scales, these will probably mean something to you. If not, we'll have to use a fancy method and enhance the situation. Oh man, I timed that wrong. And enhance again. And we are actually going to enhance it again. And we're going to go in one more time, actually, because this is just how rich this data set is. So now at this scale, you can actually start to see how resolved this fully developed turbulence is. Each one of these shapes is the core of a different vortex. And we're going to back up one. That's a little too far. What we're doing is taking a piece of that original data set and considering this our information. And so we started with one gigantic grid. We now have 512 subdomains. So just to really make this apparent what's going on. So we're chopping our grid, which is really a three-dimensional cube. We've got 512 blocks of this fluid. And we want to know, how can we use all this data to then organize statistical relationships, across the dynamics of each of these subdomains? So what physical rules or statistical relationships might we be able to uncover by examining these 512?
How do you know your numerical scheme is reliable in such turbulence? I mean, what's the check of, this is meaningful?
Yeah, I trust that it is meaningful at this point in my career, I suppose. But all I know, so to a little bit, what impresses me about this data set is I found out it was simulated using the K computer in Japan, which I guess is still like the 8th biggest computer in the world, so it's pretty big. And pretty much anybody when I say I'm using Takashi Ishihara's data, they're like, oh, okay, that's the right data then. So, I don't know, but as far as the community is concerned, it seems like everybody's okay with this particular data set.
So wait, is that a proof by reputation?
Yeah.
The really cheap answer is there's a numerical scheme that's being used, so we're analyzing the numerical scheme. Still a big
Yeah.
deal.
Yeah.
But of course, one can check things like conservation laws.
So
Of course.
Probably,
I know there are a lot of debates, or there were many years ago, around Turbulence as to the correctness of the numerics and whether things are blowing up or not. So I'm just curious whether that's an issue that you even addressed or not.
I don't know. I would have had to have gotten a different PhD to answer those questions, I think. I went the algebraic topology route. All right. So what are we going to do? We've got these 512 subdomains. I heard somebody mention Koifman and diffusion maps earlier, I thought. But perhaps we could use the diffusion maps and organize this data. So I'm not going to get into the details of it, but essentially what this picture on the right illustrates is they have shown that you can throw a bunch of different pieces of data at it. Here they have the word 3D that's been rotated by around the z-axis and around the x-axis. And after giving these pictures, you've put a kernel on that distance, a Gaussian kernel, and then you look at this sort of random walk given by this kernel distance, and you look at the eigenvalues and eigenvectors of that particular matrix. Then eventually you can project onto these first two diffusion map coordinates and see, in some sense, projection of your data which preserves local distance relations but not necessarily global ones. And most importantly, it seems to capture organization in your data, intrinsic organization in your data. And so we wondered, well, what is it going to pull out of these scalar fields? Well, one thing you have to do is choose a distance in order to actually plug into this machinery. Why not persistent homology? So we've got our scalar field. Here are our 3 persistence diagrams corresponding to dimension 0, 1, and 2 sublevel set persistence. And on the right, some pictures describing what's called the landscape distance. So the general idea is if you have this persistence diagram with the 3 blue points on it, You build these sort of tent functions off of them, tip them over, and then take the upper envelopes. So this top function, lambda 1, is the first, basically, LP function, and then the second and the third. Now you have a vector of LP functions, essentially, that you've reduced your persistence diagram to. Why would we use this particular metric? The idea is you use the LP metric on these functions. So we use this for two reasons. It's cheap to compute. Remember, we've got a lot of data here. Secondly, it naturally weights changes away from the diagonal. So if you imagine, if you move or perturb one of these points, if it's far away from the diagonal, that L1 or L2 norm between the functions is going to take the area of that entire strip. Rather than with bottleneck distance, it doesn't matter if you have small scale fluctuations near the diagonal or far away, it weights them all the same. So perhaps this is useful when trying to organize vorticity fields. Once we do this, we apply our diffusion map embedding. We use this landscape L2 distance using a Gaussian kernel, and then that epsilon parameter we just set to be the average value of the distance matrix, and we get this plot here. And our question was, what is that x and what is that y organization in the scalar fields? We were able to find these two relationships. So the right color gradient is the most striking. This is entropy, or essentially something close to the L2 norm of the vorticity field, not quite. And you've got this beautiful gradient running in the y direction. So this one we kind of cheated. We actually knew we were going to look for entropy first. So when we ran our diffusion map embeddings, we ran correlations for the rankings against entropy across all of these different diffusion map embeddings. So we were actually going out looking for some organization with entropy. It was surprising that it was so important. Second diffusion map coordinate. But what about organization along the first one? We had to back into this problem. So what we did is we used this method of extreme point analysis. When we looked at our point cloud, we said, well, what do the persistence diagrams look like all the way over to the left? This is dimension 2. What do the persistence diagrams look like over on the right? And then what is the difference between them? And you start to see, well, these are very sparse away from the diagonal. These are more dense. If you look at representative isosurfaces, so we choose the same cutoff value for representative vorticity fields and say, well, show me the isosurfaces, they're much more sparse over to the left than over to the right. And this is actually a measure of intermittency. And so essentially, yes?
Just one question. How do you know that you have just two-dimensional manifold?
Oh, we're not supposing that in the slightest. So the idea is, sometimes you'll use diffusion maps in order to try and uncover some sort of a manifold structure that's underlying your data. As a completely different way, you can just use it as an organizational tool. So we're not even assuming that there was a two-dimensional manifold there. But we wondered, could we find organization along those top two dimensions? And to some extent, we have, which is interesting. And it came from supplying the distance between persistence diagrams. So the persistence diagrams were able to encode these differences and really distill the data from these very rich scalar fields into something that then could be pulled out through data analysis. Ultimately, we got rid of persistent homology, and we were able to find this fairly robust linear relationship connecting, it's a log linear relationship connecting maximum vorticity, entropy, and then this order 10 statistic that was the highest moment that we colored our vorticity fields by. And we find this very nice log linear relationship between them. You can see the root mean square error going down, r squared going up as the order of the standard moment is increasing. Now, this might have been somewhat impressive with only the 512 scalar fields, but we did actually 4 additional time points. So this is actually a point cloud showing 2,560 different vorticity field subdomains. And so we found the relationship using just one simulation and then actually show that it also held for 4 additional simulations. So that was pretty exciting. All right, final act. combustion. So this is more work that has started with Takashi Ishihara and others. And this is very much work in progress. So again, just giving you an idea of the direction we're headed in with these types of results. So in this particular setup, we're looking at homogeneous charge compression ignition. So unlike a gasoline engine, which has a spark ignition, or a diesel ignition that has a fuel injection, homogeneous charge compression ignition, you just have a mixed fuel and oxygen in the chamber, and then you compress it until it ignites. And so the hard part about harnessing this type of combustion is controlling the timing of the onset of ignition, because you don't have direct control. And it's hard to tell exactly which variables control it. It has ultra low emissions though, it's low temperature combustion, and so if we could actually figure out how to really leverage and harness HCCI technology, it could be a big benefit. So they're very interested in figuring out how do we control the timing of ignition in pure HCCI. This scalar field gives a couple of isosurfaces of the temperature field profile throughout this pre-ignition phase of the reaction. So what's happening is you can see the chamber is starting to be compressed. Here's about when the temperature starts to kick off, and this is when the ignition is occurring in the reaction simulation. These different curves are essentially testing or working out a preliminary hypothesis by Ishihara, which is perhaps controlling the fluid flow itself, the turbulence in the chamber could affect the timing of the onset of ignition. And essentially the idea is you have on the left in blue inhomogeneous temperature profiles, also in red, but at very low initial velocities. 0, so not moving at all, and then a low initial velocity, and then a high initial velocity in red. And the idea is, well, perhaps if we take an inhomogeneous temperature field, move it really fast, then the timing of the ignition will behave as if it were a perfect homogeneous temperature field. And that seems to be the case over at the point of ignition. So this green line, you can see neither the red nor the blue follow it, but once you actually get to ignition, that red curve moves to the right and then the blue curve stays to the left. So the question is, well, now that this direction has been established, how do you actually investigate and try and figure out why this change might be occurring? And what's really affecting this? So this Tsurushima mechanism comes with a lot of data. The fuel and oxidizer, you've got N-heptane and oxygen, and then 24 additional chemical species are kept track of. So the density or the presence of those chemical species. This is across 26 different elementary chemical reactions. Plus we have temperature, heat release rate, and vorticity. So many, many, many scalar fields. Since we haven't seen enough persistent homology.
What's happening in that box?
Oh, man. Oh, what's happening?
Yeah.
Oh, you missed it. Oh, you missed it. Yeah, so this is the temperature. These are isosurfaces of the temperature.
And when it explodes is when the combustion happens?
Exactly. Yep, that's when it's going up.
The dotted lines.
Oh, man. All the effect is ruined.
The dotted lines.
Oh, I'm actually not sure. I don't know if those are some sort of variance computations. These are average profiles, so this is the average temperature. Probably has something to do. Yeah.
Why you use the like this heavy fuel that have 2 ignition stage? You can use something simple which has just 1 ignition.
You would have to ask Ishihara about that. Unfortunately, he's not here. He couldn't make it today. But yeah, those finer points I'm not sure about. Okay, are we ready for persistence now? Okay, so these are, oh no, of course. Okay, these are all of the scalar fields, and we're watching dimension 0 and dimension 2 persistent homology all at the same time. So imagine with that scalar field we saw in that box, the temperature profile, you could kind of see what was going on, but you had to choose particular isosurfaces. And you would then watch a lot of them at a time. Well, this at least removes the necessity of choosing different isosurfaces, different thresholds for which to view. but it's still way too much data to actually look at. So maybe persistence is a first step in reduction, but we want to go one step further. And really, we want to track the changes over time. So what if we use that landscape metric again and take a look at speed profiles or the distance profiles in the space of landscape diagrams? So we've got temperature on the left, oxygen on the right, N-heptane, and then CO2 is one of the resulting chemical species, and OH, hydroxide, is an intermediate chemical species. And you could see how, at first, your N-heptane and your oxygen are moving a lot. So remember, they were very high concentrations at first. This is dimension 0 sublevel set persistence. They were at very high concentrations. As soon as they start burning, you get pockets of local minima appear, which are detected by sublevel set persistence. Eventually, temperature, which starts out as a low value, actually gets mostly very hot, and then there are only isolated cold spots. And so you would expect something going from low to high concentration or low to high values would have a temperature or a persistence speed profile curve that's active in the latter half, and then something goes from high to low is active in the first half. But hydroxide is active in both. This reflects that intermediate nature of the chemical. So as soon as it appears and creates some sort of isolated local maximum, it disappears and creates a bubble. And so right behind every local maximum, a local minimum is also occurring. And so you'll see these double peaks. We can check the landscape different speed profiles across all 3 dimensions, so dimension 0, 1, and 2. And there's more evidence of this dual nature of the scalar fields going from bottom to top and top to the bottom. And this is, you could think of it, it exists because of the nature of Alexander duality, and where you can kind of think in behavior they are complements of each other, essentially. And I mean, this is all fluid flow on in a torus, so it's not going to be exact, but in spirit, you have this duality because of the complementary nature of the way the scalar fields are moving. And so what happens if we take a look at, I mean, it's way too much data, but I love looking at way too much data because you really start to see the patterns that might be there in order to pull out what's going on. So on the left, these are all of the speed profiles over 2 different velocities in the landscape metric space of persistence diagrams. On the right, we have the usual L1, L2, and L infinity speed profiles of scalar fields. So perhaps if somebody who hadn't been exposed to persistent homology were going to take this on, they'd say, well, let's just look to see how much the scalar fields are changing. Let me just look at the speed of the change in scalar fields on the right. And you can see some separation, especially in L infinity, between the stripes and then the solid lines. And this is the 2 different initial velocity conditions. But you can see much more separation in the behavior of the different chemical species over on the left using the persistence profiles, because it can actually distill the patterns that are happening regardless of those symmetries or where these local maxima might be taking place. And so you distill a lot more of the inherent nature of the chemical reactions using persistence. So it's not necessarily one set of speed profiles versus the other, but perhaps there's something you can use in this L infinity speed profile in conjunction with additional speed profiles from persistence. And so what we're looking ahead towards doing is going through each of these 26 different elementary chemical reactions, taking a look at the speed profiles of all of the chemical species involved there, and seeing how do they change based on the initial conditions. Perhaps we do a collection of runs in initial velocity 1 and a collection of runs in initial velocity 4, and then compare them to these average differences that we can pull out of these patterns topologically that we might not have been able to pull out and distinguish using just the speed profiles on the right. So here's another picture. This is a chemical reaction that's a little bit later on, but you can definitely see some clear differences. So I think we're to the point we might be able to answer the question that we posed at the beginning, which is, what is persistent homology, right? So first, we see that it's a tool for symmetry reduction. We also see that it's a tool that we can use for encoding shapes. Dare I say it, for feature engineering and machine learning. We also see that it's a metric space. We can put a variety of metrics on it, so we can use tools like diffusion maps. We can generate speed profiles from this data. We've seen how we can annotate images, and we can actually use it to annotate patterns and do computer vision problems with persistence. And then we've also seen how all of these applications have actually given rise to new theorems and new theory in persistence and TDA. So using the decorated merge tree for disambiguation and for feature tracking, and then also another piece that sits on top of actually every part of this are these rigorous error bounds. And so any computation you make along the way, if it really was important and you needed this fine of control, you could put these error bounds and get rigorous measurements all on the outside. So, the workshop title, Identifying Order in Complex Systems, we've certainly used persistence to identify some order in this complex system of fluid flow, but perhaps we've really uncovered some order in the world of topological data analysis and persistent homology by looking at it through the lens of all of these different fluid flow problems. And that's all I've prepared for you today. Thank you very much.